Here we have a bare outline of the logic underlying momentum and impulse. We start with Newton's second law. We define momentum thusly. We combine these two to get this formula for impulse, and then we use that to derive the law of conservation of momentum. In this video, I'm going to cover everything you see highlighted in red. So I'm going to define momentum, and then I'm going to show how we get this impulse formula. This is the first video in a playlist that I'm making about momentum and impulse. The second video will cover how we get from impulse to conservation of momentum. I'll be posting that in a few days, and it should be up by the time you see this. If it is, there'll be a link up there in the corner. And there's a link to the playlist as well. I'm not going to explain Newton's second law. I'm going to assume you already know that, so you know all about force and acceleration and presumably velocity. Now, when you first learned this, they may very well have started with this and then skipped straight to this without bothering with impulse. And there's a reason for that. This formula is of a lot more practical use than this, actually. There are many, many problems that you can solve using the law of conservation of momentum, whereas the formula for impulse is really only useful in a few limited special cases. So if there's room in your brain for only one of these two, it should probably be this. Maybe you need to skip to the next video. But if you actually want to understand this stuff, you need impulse, because this is the essential link in the logic that connects Newton's second law to momentum conservation. And without that understanding, you'll never really know when conservation of momentum applies and when it doesn't. So here's the definition of momentum. We use the symbol P for momentum, and momentum is equal to the mass of an object times the velocity of the object. So a mass moving along with the velocity of v will have a momentum equal to P. Velocity and momentum are both vector quantities, and velocity and momentum always point in exactly the same direction. No exceptions. People who are comfortable with this will use momentum and velocity interchangeably sometimes, because if you know the one, you know the other, as long as you know the mass. The units for momentum are simply the units of mass times velocity. Kilograms times meters per second. Kilogram meters per second. And there's no special name for this combination of units. That's what they always call it. Now suppose you have an object sailing along with a certain amount of momentum, and then a little while later it has a different momentum. So we have an initial momentum and a final momentum. What happens when we subtract P final minus P initial? Well, we just get this twice. We get mv final minus mv initial. Now I just made an important but subtle assumption here. I assumed that the final mass was the same as the initial mass. That doesn't have to be the case. But if the mass is changing over time, then things get very complicated. At the beginner level, we'll just assume that it's constant mass. So if it's constant, we can factor out that mass. And of course, whenever you've got a final minus an initial, we can call that a delta. So the delta P is equal to the mass times delta V. What good is that, do you suppose? Well, let's take a look at Newton's second law. Acceleration, of course, is the rate of change of velocity, which is the change in velocity divided by the change in time. I hope you see where I'm going with this. We have a perfect match between this expression and that. So we can actually replace that. And we will get force equals delta P divided by delta T. And from there, it's easy to see delta P equals F times delta T. The change in momentum, or momentum change, is what we call impulse. Anytime an object's momentum changes, there is an impulse. And even if the momentum doesn't change, there's still an impulse. It's just equal to 0. Now, for some reason, some teachers, some textbooks prefer to use the letter J for impulse. So you'll sometimes see this. You should be aware that there's nothing special about this J. It's just another way of writing delta P. I don't care for the J because I think that delta P gets the job done just fine. And honestly, I don't even really care for this word impulse too much because we already have a name for this. It's momentum change, or change in momentum. So everything I've highlighted in red here, strictly speaking, is redundant. You don't actually need to know any of this to solve problems. But if your teacher includes the word impulse or the letter J in the curriculum, then of course you need to know it. If you see the word impulse in a test question, you need to know what that means. Now, I was going to do an example problem using this impulse formula, but I decided not to, partly because it just made the video too long, and also because it's not really necessary, because the impulse formula is really just Newton's second law all over again. So any problem you can do using the one, you can do using the other. If anyone out there is interested in seeing such an example, let me know in the comments, and I'll look into it. Now, as I said before, there's not a lot of practical use for impulse all by itself. The whole point of this video was to be a warm-up for my next video on the law of conservation of momentum. So I suggest you go have a look at that now. Thank you very much for watching. Please like and subscribe. Also, if you would like to be tutored online by me personally, I am available. You can find a link to that information down below. And also, here's a link to that playlist I mentioned.